If I asked you right now to come up with a way to estimate Earth's age, what would you do? No clue? Don't worry. In this video, we're going to dive into how humans gradually figured out the true age of our planet. Before we get into the methods, there's one important concept to establish. Earth, like humans, animals, and plants, has a birth date. It wasn't always here, it had a beginning. And once people realized that, they started trying to figure out when that beginning was. The first serious attempt to determine Earth's age came from an Irish archbishop named James Ussher. He was a highly respected scholar at the time and loved studying ancient texts. While going through historical records, he noticed that if he pieced together different timelines from old scriptures, he could actually map out a potential birth date for Earth. Excited by his discovery, he carefully compiled his findings and, in 1645, published a book called The Annals of the World. His conclusion to Earth was born on October 22, 4004 BC, on a Saturday around 6 p.m. At the time, this idea gained traction because most people didn't have a strong scientific background. They relied on religious texts and historical records, so Ussher's theory became widely accepted. But as time went on, more and more people began to question whether myths and ancient texts were really a reliable way to determine Earth's age. Scientists started searching for more concrete scientific methods, ones based on actual evidence rather than written records. In the 18th century, a French naturalist named Benoît de Maillet became the first person to estimate Earth's age using geophysical evidence rather than ancient texts. His reasoning was surprisingly simple. No matter where you go, whether it's the Himalayas, the Gobi Desert, or the Alps, you can find seashell fossils embedded in rocks. Based on this, de Maillet proposed a bold theory. Earth was once completely covered by water, and all life evolved from the ocean. This idea was incredibly ahead of its time, so his method was straightforward. If the planet was once submerged and the ocean levels had gradually receded, then by calculating the rate at which sea levels dropped and comparing it to today's sea levels, he believed he could determine how long it had been since Earth's surface became dry land. His conclusion to the age of Earth was around 2 billion years old. At the time, this number was unbelievably massive, especially compared to James Ussher's estimate of just a few thousand years. The leap from thousands to billions was shocking. Mathematically, de Maillet's logic was solid, but there was a major flaw in his assumption. Sea levels hadn't actually changed that dramatically over time. The real reason we find seashell fossils in mountains and deserts isn't because the oceans receded. It's due to the movement of Earth's tectonic plates, which pushed ancient seabeds up to form land. Even though de Maillet's estimate was based on a mistaken premise, his approach was groundbreaking. For the first time, someone attempted to calculate Earth's age using scientific observation rather than religious texts. You've probably heard of Charles Darwin, but did you know he had a son named George Darwin? Unlike his father, who revolutionized biology, George took a different path. He was fascinated by geology and the moon. George Darwin had an interesting theory about how the moon was formed. He believed that the reason the moon is tidally locked to Earth, meaning the same side always faces us, is because it was once part of Earth. According to his idea, when Earth was newly formed, it was spinning at an incredibly high speed. Over time, as Earth's internal energy increased, some of its material was ejected into space, forming the moon. After that, Earth and the moon began gravitationally influencing each other. The moon gradually slowed down Earth's rotation until it settled into the 24-hour day we experience today. Based on this theory, George did some calculations and estimated that for this Earth-Moon system to evolve to its current state, it would have taken at least 5,600 years. So, he concluded that Earth's age must be around that number. Both George Darwin and Benoît de Maillet based their calculations on assumptions, essentially using imagination rather than hard evidence. Naturally, this made their estimates less reliable. But just 2 years after George Darwin published his theory, a German geologist named Johann Joly proposed a different method to estimate Earth's age, one that sounded much more scientific. His idea was simple. Many geologists at the time believed that the salt in Earth's oceans came from rivers slowly eroding rocks and carrying minerals into the sea. If that were true, then by calculating the rate at which salt accumulated in seawater, he could estimate how long this process had been going on, essentially the age of Earth. After running the numbers, Joly came up with an answer: 89 million years. At first glance, this made a lot of sense, but there was one huge problem. Even today, we still don't fully understand whether the salt in our oceans is entirely from river erosion, or if Earth's oceans were already salty from the very beginning. By the early 19th century, most people in Britain had already accepted that Earth's age was likely far beyond human comprehension. This shift in thinking was largely due to discoveries made by geologists in the late 18th century. They realized that geological processes, like the formation of rock layers and the erosion of landscapes, took an incredibly long time. These weren't events that happened overnight, or even in a few thousand years. One of the biggest clues came from fossils buried deep within rock layers. When scientists excavated these fossils, they found that many belonged to creatures that had lived and died long before human civilization even existed. In 1795, a Scottish geologist named James Hutton introduced a groundbreaking idea in his book, the theory of uniformitarianism. The core idea behind uniformitarianism was simple but revolutionary. Geological processes happen extremely slowly, so slowly that human lifetimes are just a blink in comparison. Mountains don't rise overnight, rivers don't carve canyons in a few years, and rock layers don't form in a single generation. This theory quickly gained popularity, and by the 19th century, most geologists had accepted it. But it was Charles Lyell who truly brought uniformitarianism into the spotlight. Lyell wasn't just a scientist, he was an incredible writer, and his book, Principles of Geology, became a bestseller, reprinted multiple times. Even Charles Darwin carried this book during his famous voyage around the world. Darwin later developed his own theory of natural selection, arguing that evolution was also a slow and gradual process, just like geological changes. His studies in geology even helped him support his evolutionary theory. Using geological evidence, Darwin made a bold estimate. Earth had to be at least 300 million years old. Even though Darwin and Lyell were on the right track, there was one major problem. They didn't have any hard data to support their claims. At the end of the day, their theories were still just educated guesses without solid proof. This didn't sit well with Lord Kelvin, one of the most respected scientists of the time. He believed that science had to be precise and based on measurable data. You couldn't just rely on intuition or logic alone. Kelvin didn't hold back. He publicly criticized the geologists of his time, including Darwin, calling their theories wild speculation. He argued that science isn't about imagination. It's about numbers, calculations, and real-world evidence. And, honestly, he had every reason to be skeptical. At the time, Kelvin was already a pioneer in thermodynamics. The concept of absolute zero, as well as the first and second laws of thermodynamics, were all his contributions. Even today, we still use the Kelvin temperature scale in scientific research. But Kelvin didn't just question others. He set out to prove them wrong by calculating Earth's age using real scientific data. Since no one had accurately calculated Earth's age using real scientific data, Lord Kelvin decided to do it himself. And for a legend in thermodynamics, this was just another problem waiting to be solved. At the time, coal miners already knew a basic fact. The deeper you go underground, the hotter it gets. Kelvin understood that this heat came from Earth's core, meaning the interior of our planet must be extremely hot. Based on this, he proposed a bold idea. What if Earth started out as a massive ball of molten rock and had been cooling ever since? If that were true, then by calculating how long it took for Earth to lose its initial heat, he could determine its age. To do this, Kelvin set up a mathematical model for Earth's cooling process. He needed 3 key pieces of data. 1. Earth's initial temperature, how hot it was at the beginning. 2. The The thermal conductivity of rocks, how well heat moves through Earth's layers. 3. The temperature difference between Earth's core and surface. With this information, he believed he could finally calculate how long it took for Earth to cool down to its current state, and in turn estimate its true age. Like the scholars before him, Lord Kelvin had a big problem. He had no idea what Earth's original temperature actually was. But being a master of thermodynamics, he made an educated guess. He assumed that Earth started out at around the melting point of rock and used that as his initial temperature for the calculations. His first estimate to the age of Earth was 100 million years. But as he refined his equations and considered more variables, his answer kept changing. Over time, his estimates ranged anywhere between 20 million and 400 million years. Even Kelvin himself started to lose confidence in his calculations. Despite this, his massive influence in the scientific community made people believe that his physics-based approach was the most reliable method available. For a while, his numbers were considered the most authoritative estimate of Earth's age. But his dominance didn't last long. In 1899, geologist Thomas Chamberlain directly challenged Kelvin's theory in a published paper. He argued that Kelvin was oversimplifying things and that Earth's interior was far more complex than he assumed. In 1896, physicist Wilhelm Röntgen made a groundbreaking discovery: X-rays. He found that these mysterious rays could pass through black paper and reveal hidden objects, sparking excitement in the scientific world. One person who took immediate interest was Henri Becquerel. He suspected that Röntgen's discovery might be related to his own research. That same year, Becquerel made a huge breakthrough. He discovered uranium's radioactivity. His conclusion? Radioactivity was a property of uranium itself. It didn't need any external energy source to emit radiation. This discovery was so significant that the unit for measuring radioactivity, the Becquerel, was later named after him. But the story didn't stop there. Soon after, Marie Curie and her husband, Pierre Curie, identified two more radioactive elements: polonium and radium. It wasn't until later that scientists realized the true impact of these discoveries. Earth wasn't just cooling down over time, as Lord Kelvin had assumed. Deep underground, radioactive elements were constantly generating heat, along with the heat from Earth's core. Kelvin had never accounted for this, and to be fair, he couldn't have known. Radioactivity hadn't been discovered when he made his calculations. But this new knowledge didn't just prove Kelvin wrong, it also gave scientists a brand new way to estimate Earth's age. At the same time, it marked the beginning of the nuclear era, with radioactive elements stepping onto the stage of history. In 1901, as the world stepped into the 20th century, two scientists, physicist Ernest Rutherford and chemist Frederick Soddy, began conducting a series of experiments on radioactive elements. What they discovered was revolutionary. They found that radioactive elements don't stay the same forever. Instead, they spontaneously transform into new elements, releasing radiation in the process. This meant that radioactive decay was a natural, unstoppable process where unstable elements gradually turned into stable ones. But that wasn't all. After years of continuous research, they noticed something incredible. The radioactive activity of a sample always decreased in a predictable way. It would drop by half over a specific period of time, then continue decreasing at the same rate. This discovery became known as the half-life, a fixed, measurable pattern that determined how long it took for half of a radioactive substance to decay. And then, Rutherford had a light bulb moment. This wasn't just a cool scientific observation. It was a natural clock. If scientists could properly measure the half-life of radioactive elements, they could use it to accurately determine the age of Earth's rocks. Following this breakthrough, Ernest Rutherford turned his focus to studying uranium-rich rock samples. He wanted to see if he could apply the half-life principle to measure Earth's age. His approach was simple but brilliant. Uranium decays into helium over time. By measuring the amount of helium trapped inside these ancient rocks, he could estimate how long the decay process had been happening, essentially, how old the rocks were. After running the calculations, Rutherford arrived at a staggering number, 500 million years. However, he knew his estimate was probably too low. Since helium is a gas, some of it could have escaped from the rocks over time, making the measured amount smaller than it should be. This meant the true age of Earth was likely even older than 500 million years. Rutherford's method of using half-life to determine rock ages was a major breakthrough, setting the stage for future discoveries. But over the next few decades, scientists ran into a new challenge. While they could measure the ages of different rock samples, their results didn't always match up. Despite the inconsistencies, one thing became clear. Earth's age wasn't in the millions, it was in the billions. The technique, known as radiometric dating, worked by measuring how much of a radioactive isotope had decayed into a stable element. This was clearly the right path forward. But physicists now faced the same problem early scientists had struggled with. How could they find a sample that truly represented Earth's original material? Digging up Earth's own rocks wasn't a reliable option. Earth is geologically active, meaning that most rocks on the planet have been recycled, melted, and reshaped over time. Finding a piece of Earth's original crust was nearly impossible. That meant all the efforts so far were only measuring the ages of specific rocks, not the age of Earth itself. So, where could scientists find a sample from Earth's earliest days? One that hadn't been recycled by geological activity or contaminated by human influence. The answer wasn't on Earth, it was in space. Astronomers believe that all celestial bodies in the solar system formed around the same time. That means asteroids and Earth were born together. Unlike Earth, however, asteroids remain largely unchanged, drifting through space without being affected by plate tectonics or erosion. So, if scientists could analyze the rock from an asteroid, they could determine the true age of our planet. But sending a mission to collect asteroid samples was out of the question at the time, so they found a much simpler solution. Meteorites. Pieces of asteroids regularly fall to Earth as meteorites. By finding and analyzing a meteorite from space, scientists could finally determine Earth's true age, without needing to leave the planet. And now, we finally arrive at the main character of this story, Clair Patterson. Patterson dedicated his entire life to researching isotopes, and in his early work, he and his partner chose to study zircon crystals. Why? Because zircon had a very special property that worked in their favor. It strongly rejected lead, but readily accepted uranium. This meant that any lead found inside zircon had to come from radioactive decay, a perfect natural clock for measuring the passage of time. Patterson placed huge hopes on zircon, but after 5 long years of experiments, he never got a completely clean sample. Every time he ran tests, his results were all over the place. In 1953, he moved to Caltech, where he finally got the chance to build one of the world's first ultra-clean laboratories. This lab eliminated contamination, giving him the precision he needed. Now, he had the lab and the zircon samples, but there was still a major problem. None of the samples came from Earth's original crust. They had all been reprocessed by Earth's active geology. In fact, it wasn't until the early 21st century that scientists found a 4.4 billion-year-old zircon crystal. Since zircon wasn't giving him the answers he needed, Patterson decided to look beyond Earth. His opportunity came when he got his hands on a 60,000-year-old iron meteorite from his professor. This meteorite contained very little uranium, but it did have lead isotopes that had been locked in place since the formation of the solar system. And that was exactly what scientists had been searching for all along, a way to determine Earth's original lead isotope ratios. Using this meteorite, Patterson finally arrived at a number, somewhere between 4.1 and 4.6 billion years. But that still wasn't accurate enough for him. Over the next several years, he continued refining his data by analyzing more samples. Finally, in 1953, Patterson published the most precise estimate yet: 4.55 billion years, give or take 70 million, This number has since been confirmed countless times by later scientists with almost no deviation. Patterson had cracked the mystery of Earth's age. But his work didn't stop there. During his research, Patterson accidentally uncovered one of the biggest public health crises of the 20th century. He discovered that modern humans had 1,000 times more lead in their bodies than ancient humans. He also found that lead pollution in the environment had skyrocketed. Where was all this extra lead coming from? Lead additives in gasoline. For the next few decades, Patterson fought against the powerful oil industry, exposing the dangers of leaded gasoline and pushing for its ban. His relentless battle eventually led to the introduction of unleaded gasoline, changing the world forever. And today, if you look at any gas station pump, you'll see the label, unleaded fuel. And for that, we have Clair Patterson to thank. Thanks for watching. If you enjoyed this story, don't forget to like, subscribe, and leave a comment. I'll see you in the next one.